Let's jump right in, because today's explainer covers a truly massive macro-to-micro leap in quantum mechanics. We're taking something you'd normally see ripping across the plains in a massive thunderstorm, and we're shrinking it all the way down to the level of individual photons. It's an absolute breakthrough, and it could completely rewire how we think about quantum communication and next-generation photonics.
Okay, let's dive into this. Can light actually spin like a whirlwind? I mean, it sounds a bit like science fiction, right? We're so used to light just moving in straight lines, or, maybe bending through a prism. But twisting into a miniature optical tornado? Well, researchers from the University of Warsaw, the Military University of Technology, and CNRS over in France have proven that not only can it happen, but we can actively control it. Now, to understand exactly how they pulled this off, we first need to get a grip on what an optical vortex actually is. Dr. Marcin Muszyński, the lead author of the study, explains it like this. It's essentially a structured light wave, but as this wave travels, it twists around its own axis. The phase actually changes in a spiral. And it goes even further than that, even the polarization, which is the actual direction the electric field is oscillating, begins to rotate. So just picture a corkscrew made entirely out of pure light energy. Pretty wild, right?
So how do we get to the structured light? Well, the desire to create these states isn't exactly new. Scientists have been chasing this for a while because these optical vortices are incredibly useful for quantum communication and manipulating microscopic objects. The catch, it has traditionally been incredibly difficult to actually pull off.
Now, what's really interesting about this slide is the sheer, stark contrast between the old way of doing things and this new strategy. To make an optical vortex in the past, scientists had to build incredibly complicated, super expensive nanostructures, or rely on these massive, clunky experimental setups. But the team at the University of Warsaw, they took a really elegant shortcut. Instead of all that heavy machinery, they turned to a material most of us are literally staring at right now on our monitors and TVs: liquid crystals.
Joanna Medricka, who helped prepare these samples, gives us a really brilliant visual for how this works. You see, liquid crystals can flow like a liquid, but their molecules arrange in a highly ordered, structured way. When special defects form in the crystal, the molecules arrange themselves into tightly twisted spirals, kind of like a stranded DNA. Then, the ends of those spirals join together to form a closed ring. Basically, it's a microscopic donut. In physics, they call this a toron, and as you can see, this little molecular donut acts as a perfect microscopic trap for light. Let's move on and see how this builds, because now we hit a major hurdle. We have our trap, sure, but how do we force the light to actually spiral inside it? If we were dealing with electrons, it'd be a piece of cake. You just turn on a magnet and the electrons curve. But photons, particles of light, they literally don't care about magnets. They don't react to magnetic fields at all. So the researchers had to somehow create an impossible field.
Dr. Piotr Kapuściński perfectly summarizes how they managed to solve this puzzle. He notes that something called spatially variable birefringence acts as a synthetic magnetic field, meaning it physically isn't there, but it tricks the light into bending, almost exactly like an electron caught in a cyclotron orbit.
Okay, let's demystify that heavy physics term for a second. Spatially variable birefringence. I know, it sounds super intimidating, but it simply means that different polarizations of light travel differently through the liquid crystal. By carefully structuring the material, the researchers essentially created a mathematical equivalent to a magnetic field. They aren't using actual magnets at all. They're using the geometry of the liquid crystal itself to steer and twist the light. It's just incredibly clever.
And to make sure the trap really holds on to the light, the team placed the Toron inside an optical microcavity. Think of this as a tiny room made of mirrors. The light just bounces back and forth, continuously passing through that liquid crystal donut, which completely supercharges the twisting effect. And honestly, the best part? They can control the exact size of the trap and the properties of the light just by tweaking an external electric voltage.
But setting the trap and twisting the light was really only part of the battle. What elevates this research from a neat laboratory trick to a massive breakthrough is what happened next. This is kind of the absolute climax of their experiment.
They actually achieved stable light vortices in the ground state. Professor Guillaume Malpuch, who helped develop the theoretical model for this, pointed out that in typical systems, if you want light to carry this kind of twisting orbital angular momentum, you normally have to pump it full of energy into highly volatile, excited states. But this team, they achieved it at the absolute lowest possible energy state.
So, the crucial point is, why do we care about the ground state?
Well, a few big reasons. Because it's the lowest energy state, it is incredibly stable. And because it's stable, energy naturally wants to accumulate right there. And since the energy accumulates there with such low losses, it makes it remarkably easy to achieve coherent lasing. The light naturally wants to be in this swirling, stable condition.
To prove just how incredibly stable this setup was, the researchers went ahead and introduced a laser dye into the system. The result? They produced exactly one coherent beam of light, just a single perfectly rotating optical tornado with a strictly defined energy and a precise emission direction. They had successfully built a microscopic, structured laser using self-organizing liquid crystals.
So, looking toward the future of quantum tech, let's zoom back out to the macro level for a minute. What does a tiny liquid crystal donut trapping a swirling photon actually mean for the rest of us? The implications here for the future of technology are absolutely massive. And this brilliantly illustrates how we're opening up a massive new frontier. We are entering an era of quantum computing and advanced optical communications, and those fields require us to manipulate light in highly complex ways. By proving we can basically skip the ridiculously expensive and complex nanotechnology and instead use self-organizing materials that naturally form these structures, we found an entirely new, highly scalable pathway. We can build simpler, smaller, and vastly more efficient photonic devices.
I want to wrap up by leaving you with this truly mind-bending quote from Prof. Dmitry Solnishkov. He noted that their approach draws from such advanced physics that, quote, "We've managed to make photons behave not even like electrons, but like quarks, the charged particles which make up protons." I mean, just think about that for a second. Using simple liquid crystals and mirrors, we are literally forcing pure light to mimic the absolute fundamental building blocks of reality. If we can make light act like the very foundation of matter itself, what other impossible things can we trick it into doing next? Thanks for joining me on this deep dive into the explainer. Keep asking questions, and I'll catch you next time.